First of all, we need to describe some examples of oscillations. An oscillation is a cyclical disturbance of a body in a medium around a fixed point or value. Some examples. A child's swing oscillates when pushed. Its equilibrium position is when it is hanging vertically, and when you make some disturbance, you push it to the left, for example, it will move back again to the right, then to the left. So it undergoes a cyclical movement around the vertical. A tethered trolley. This is an example of a tethered trolley. You have a trolley which is tethered between two vertical poles, which means it's fixed by a spring on either side. When you hold it to the left, as it is now, there will be a force acting to the right. When it goes to the right to the other side, there will be a force to the left. So it will keep on oscillating between those 2 points. The equilibrium position will be in the middle between these 2 points. Voltage in a CR circuit, when the current moves around in an AC circuit, it goes one direction, then back again, then one direction and back again. This is also an oscillation. Define the terms displacement, amplitude, frequency, period, and phase difference. The displacement. This is a distance and direction that an oscillating system is from its equilibrium position. So it is a vector. It has magnitude and direction. The amplitude. This is the maximum displacement of an oscillating system from its equilibrium position. The frequency. This is the number of complete oscillations made by a system per second. The period. This is the time taken for the system to do one complete single oscillation. The phase difference can be viewed in a number of ways. It can be measured in radians, degrees, or fractions of wavelengths. It's basically the difference between corresponding parts of different waves, and it's measured in some kind of angle or fractions of a wave. For example, when a crest meets a crest, the phase difference is 0. But if a crest meets a trough, the phase difference in radians will be pi radians. In degrees, it will be 180 degrees. In numbers of wavelengths, it will be half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths. Now, frequency and period are linked by this equation, which is the frequency is equal to 1 divided by the time period. This is an important equation. Omega is equal to 2 pi f. Now, the omega is the angular speed, sometimes called the angular velocity. It's how much the angle is swept out per second, and it's measured radians per second. It can be degrees per second, but we use the unit radians per second. F stands for the frequency. To give an example, a roundabout spins round at a frequency of 2 Hz. What will the angular speed be? Well, if it were 1 Hz, it would sweep through 2 pi radians in 1 second. And this is 2 Hz, so in 1 second it spins around twice. So it's 2 lots of 2 pi. So it would be 2 pi times by 2, which would be 4 pi radians per second. Defining simple harmonic motion. This is the key equation for this topic. The equation is A is equal to negative omega squared x. So a system is in simple harmonic motion if the acceleration is directly proportional to its displacement and is always directed towards the equilibrium position. And this is the equation, and we'll define the terms here. A is the acceleration, x is that displacement, omega is 2 pi f, which is the angular speed or the angular velocity. And one important factor here is the negative sign. This tells you that the direction of the acceleration is always in the opposite direction of the displacement. If the swing is displaced to the right, the acceleration will be to the left. The restoring force will be to the left, always in the opposite direction to the displacement. So that's why it's negative.